Alright, so today we are going to get started on the final part of our separations homework for the semester. And I'm just going to read the problem statement here because we have a very long problem statement. So to get started, we want to simulate the dynamic response of a 7-stage distillation column with a total condenser and reboiler. Ignore vapor phase dynamics, and we are assuming a perfect controller that supplies vapor flow from the reboiler to the condenser at the combined reflux and distillate flow rates. We're also going to assume liquid overflows all units following the Weir formula, where M and M naught are instantaneous and nominal maximum holds up at flow 0, or 0 flow. M0 are 10, 20, and 30 kmol for the stages, condenser, and reboiler respectively, with 1 kmol per second of feed entering the fourth stage at Q equals 90 mole percent liquid and Z equals 0.45. We want to simulate how the compositions and holdup of the column evolve over time if the reboiler stages are initially overfilled by 10% and with a 15 kmol of liquid at the feed composition. And then the condenser is initially loaded to achieve overflow consistent with a reflux ratio of 2 and distillate flow 55% of the feed flow rate. To simplify this problem, we want to assume a binary system with a constant relative volatility of 2. Alrighty, so let's get started with the code here. And what we're doing is really just defining all of our constants or what was given to us in the problem. So what we're going to do is combine all of these constants that we have, where we have the M naught in our condenser, and then we have N times our M naught stage, and then we have our M naught in the boiler. So that's it for that part. And then we have to add a correction factor to it, and this will be our M initial, or really our guess value, where we have an MP.R underscore R initial plus 1 times DSP divided by C to the 2/3 power plus our M naught in our condenser. Then we have N times 15, and then finally 1.1 times our M naught in the boiler. So yeah, that should be all right there. And then we want to print M initial to make sure our array comes up correctly, in which it does. So now what we're going to go ahead and do is we are going to really get into defining some functions. And what this function is actually going to do is it's going to create new functions for our system. We're going to do y1, y1, or y2, t1, t2. So we define that, and then we define ramp with respect to t. And if t is less than t1, we return y1, and if t is greater than t2, we return y2. And oh, that should be y2. I don't know why it's doing this. Did I put y12 on accident? Oh, that's why. Okay, yeah, so it should be y2. And we also want to return y1 plus y2 minus y1 times t minus t1 divided by t2 minus t1. And then we want to return ramp. Alright, so for the next part, what we want to do is we define ramp as ramp underscore factory 2, 5, 10, and 30. Then we're going to do what we've done previously and define a right-hand side for our function where we have t in vector, and our r will be our r initial, and our m will be vector. Then we have our L value, or liquid, which is C times MP dot where M is less than M naught, 0, M minus M naught to the power of 1.5, and we have D, which equals L list naught, list 0, divided by R plus 1. And now we have our V rectifying, which equals R plus 1 times D. And then we have our V stripping, which equals V rectifying minus 1 minus Q times F. Now we get into a bunch of differential equations. So we're going to start with dm equals np dot zeros like m, and then we have dm equals l dm 1 colon l yeah, that should be right. Okay, and then we have dm list 1 is d. Alright, so now we have dm colon n feed minus 1, correct, and then we have dm colon n feed this one is n feed colon minus 1, I believe, and that will be plus equals v strip. Okay, now we have dm 1 colon n feed minus equals v rect dm n feed colon equals v strip. We have dm n feed plus equals n feed plus equals q times f. Let me make sure. Yep, that all looks correct. So now to finish off, we have dm n feed minus 1 plus equals 1 minus q times f plus v strip, and then we return dm. So we have an invalid syntax. I think that's just because we have that there on accident. Let me double check that. So the problem was we forgot an L in front. So now we're going to do a little more guessing. So we have to define an x initial value. And here we're going to do np.full underscore like, and it'll be m naught in our zf. Then we have a tendency. We're going to do 200. I think that, yeah. And so we have a t plot, which equals np dot line space 0 tendency 200 And then we have res equals p dot integrate dot solve underscore IVP. Right hand side 0 tend why not is equal to m initial method equals redow and dense underscore output equals false. And then we have ms is equal to res.sol tplot. Let me double check. All right, so we got that to work. So now we're going to do our plot equals mp.array, and we'll do our function ramp for t, and then for t in tplot, shift enter that, and now we're going to make our first plot. Fig equals make underscore subplots, rows equal 1, columns equal 2. Enter that, and then we're going to do for I comma m and enumerate ms. We're going to do fig dot add underscore scatter x equals tplot, y equals m. Name for this will be function I. That needs to be in I. This will be row equal 1, column equal 1. Alright, and then we're going to do fig dot add underscore scatter on the outside of this where we have x equals tplot, y equals rplot. We have row equals 1, column equal 2. And so let's shift enter this. And here we can see our first plot. Alright, so here is our plot, but what I'm going to do is I'm going to update the layout to see if this helps us see it any better, because for some reason it wants to scrunch up like this. We shift enter that. No, that doesn't really help. Anyway, it doesn't really want to expand. But as you can see, when we first make this change on our controller, we do get these steady state values, but eventually they do come back up to, or we get unsteady state to start with, but they eventually do come back up to steady state, which explains the oscillations. And there is a small oscillation here as well, if you were to zoom in on it. So there's a small oscillation to deal with there. Yeah. Alright, so now to get to our second simulation here, we're going to start again by defining right-hand side, but we're going to set this as right-hand side 2. And we're going to do t comma vector again. And we have a, which equals alpha times q minus q. And we have bb, which equals alpha minus alpha times q, plus zf minus alpha times zf plus q. Then we have cc, which is equal to negative zf. And then we have xf, which equals negative bb plus mp dot square root bb to the power of 2 minus 4 times aa times cc. and that will be divided by 2 times AA. Then we have YF, which equals alpha times XF divided by 1 minus XF plus alpha times XF. And then we need to define our R again, which will be R initial. And then we're going to have X and M be our MP dot split vector, and we want to split this into 2. And we have Y, which equals alpha times X divided by 1 minus X plus alpha times X. And now again, we want to define L, which equals C times NP dot where M is less than M naught, and then 0, M minus M naught, and this will be to the power of 1.5. And so what we're looking at now is the Weir formula. That's pretty much what we just put in, and that's the power of 1.5 kmoles per second. So just so we understand where that is coming from, so then we have L divided by R plus 1. You have your rectifying volume, which is your R plus 1 times D. Then you have your V stripping, which equals V rectifying minus 1 minus our Q times F. And we can go back into our DM equations, and we have MP dot zeros underscore like, and we're going to do like M. And then we have dm minus equals L. We have dm 1 colon plus equals L colon negative 1. And then we have dm1 minus equals D. So moving through, we have a bunch more of these to do. Plus equals our vrec. And it all looks super similar to what we've been doing. We have our dm and feed colon 1, or sorry, colon negative 1. And that is plus equals our V stripping. So we have dm 1 colon and feed minus equals V rectifying dm and feed colon V stripping. Still moving forward with these equations, we have dm and feed plus equals Q times F. And then we have dm and feed minus 1, which plus equals 1 minus Q times F. Then we have dxm, which equals MP dot zeros underscore like M. And we're going to do dxm minus equals X times L. We have dxm 1 colon is equal to or plus equals X colon negative 1 times L colon -1. So it's dxm, and then we have dxm again. 1 minus equals x 0 times d. Then we have more of these. Colon and feed -1 equals, or plus equals y 1 colon and feed times v rec. And then we are going to do the same thing here. Plus equals, do y time, and that's 1 colon, sorry, and feed plus 1 colon, close that, and then that's times v stripping. And then we have kind of similar stuff, but it's going to be dxm again. 1 colon and feed, close, minus equals y 1 colon and feed. That's times v rectifying dxm, and that is n feed -1 minus equals y n feed colon times v stripping. I think I did that right. Well, we'll hope I did. Then we have dxm and feed plus equals x f times q times f. Then we have dxm and feed -1 plus equals y f times 1 minus q times f plus y and feed times v stripping. Okay, and now we have just dx equals dxm minus x times dm divided by m, and then we want to return np dot r underscore dx comma dm. There's no way I did that. I did that all right on the first try. I'm so proud of myself. Alright, so last couple parts here, we're going to set the tendency equal to 5,000. T plot is equal to np dot line space 0 tendency 200, and then res equals sp dot integrate dot solve underscore ivp. Same old process here. RHS2 comma 0 tend, or not comma, parenthesis. My brain's getting fried from coding. I don't like coding, Carlos. Please stop. Well, I'll be done after this. So .r underscore x initial comma m initial. I'm definitely gonna spell something wrong. Method equals reval dense underscore output equal to false. I'm sorry, this time we are actually going to dense underscore output equals true. And then we are going to do xs comma ms is equal to np dot split parenthesis res dot sol, another parenthesis t plot comma 2, comma, axis equals 0. Oop, it should be t plot, comma, then 2, comma, axis equals 0. And we'll shift enter that. Okay, let me come back. Okay, so we got that portion figured out. Now for the final part of this assignment, we're gonna make our plots where we have one row, 2 columns, and we're gonna do for I, comma, x, comma, m inside that, and enumerate, zip, parentheses, xs, ms. We have fig.add underscore scatter x equals t plot, y equals x, name equals f, parentheses, x, I, row equal 1, column equal 1, close that, and we're going to do fig.add underscore scatter again, and we have x equals t plot, y is equal to our m values here, and we have a name for this, and this name will be function. Yep, looks like Colab got that all right. And let's just shift enter this and see what name mx is not defined. This should be. This is not right. This should be xs comma ms. Shift enter. Oh. Let's get the figure to show. Okay. So what we see here now. Alrighty, so from our plot here, we can now see how that responsiveness occurs within our distillation column. And according to our problem statement over here, I'm going to pull it up to recall exactly what we're looking at here. So we wanted to simulate how the compositions and holdup of the column evolve over time. If we look at the reboiler stages being initially overfilled by 10%, and we have 15 kmols of liquid at the feed composition. So you can see all of these different stages we have. It looks like we have, I'm just gonna try 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like we have about 9 stages, if I'm correct. And so we can see they all kind of start out in that unsteady state. They all have this initial oscillation, whether if it's negative or positive. But then we all see that it eventually comes out to steady state flow. So when we change our controller on our distillation column, we do see that initial unsteady stateness, I guess we can call it, and that occurs with all controllers because you're putting in an initial, or you're changing the initial going in, so you're going to see some unsteady changes there. Alrighty, so that wraps up separations part B for homework 4, and that is our final assignment for this semester. So Carlos, if you're watching this, thank you for a great semester for both classes. I did, in fact, learn quite a bit, especially for distillation columns, because I know that's going to be extremely important later down the road. But I did really enjoy separations. Obviously, like I mentioned before, I'm not a coding fan, but yeah, so thank you guys.